everybody. Thank you for this nice introduction. So it was the subject of my first slide, so okay, I can skip it. And today, so maybe I can introduce the people working on this in this lab. So Attilio Di Pietro, who I'm co-leading this group. Vincent Chaptal, Hélène Corté, and Sandrine Magnard and Frédéric Delorme from University and CNRS, and PhDs, Arnaud Kilberg, Lorena, Elodie Sougens, Zéophile Arnaud, and also postdoc Lucia Gonzalez here. So my focus today will be on drug resistance mediated by ABC pumps. So detoxification is a natural process in which ABC transporters are involved in this phase 3 of detoxification, mainly the P-glycoprotein, also called ABCB1, for which the role has a role to detoxify xenobiotics. There is also endobiotics for which the cells has to be detoxified, and this is done by other ABC transporters like MRP1, a multidrug resistance protein 1, also called ABCC1, or the breast cancer resistance protein ABCG2. The first is detoxifying the protein C4, and the other transport porphyrins and vitamin B2. The ABC transporter family is very large. In fact, apart in human, where the largest family is the GPCR1, in the other species, this ABC transporter family is the largest one. In human, it accounts for 48 members, classified from A to G classes, and they are all organized with the same compounds and the same elements of a nucleotide binding region and a transmembrane region. The NBD share a rather good identity. The identity is less good for the TMD because of the drug specificity, of course. And there is a tight coupling between ATP hydrolysis and a flux of solute. These compounds can be very different, where we found here ions, sugars, lipids, amino acid, peptides, organic molecules, and of course drugs. The topology of this transporter is schematized here. So we have always the minimal topological element is one transmembrane region here linked to a nucleotide binding region, either at the end of the TMD or at the beginning. And the functional unit is 2 times this topological unit, either organized like that or like that, and sometimes homodimeric or heterodimeric. We have also the same functional unit as in a single polypeptide, like for PGP or MRP1 or MRP2, or in this ABC transporter from the yeast, Candida albicans. In a lab, we are working on all these proteins, mainly for crystallization, for structural purposes, BMRA from Bacillus subtilis. We are also trying to crystallize the BCRP, human BCRP, on which we are working on the function and the development of specific inhibitors. The same with the PGP, for which the structural aspects are mainly developed with Geoffrey Chang, and of course MRP1 and MRP2. And more recently, we have started a study of the CDR1P, which confers resistance to Candida albicans to antifungal drugs. This is done in collaboration with Rajendra Prasad in India and Anna Shikrova in Czech Republic. I have put here the 2 main conformations in which these transporters have been crystallized. The first one in 2006 in the outward-facing conformation, and more recent, not more recently, but one of these more recently crystallized in this inward-facing conformation. The NBDs here in this conformation, outward-facing conformation, are close together. In this conformation, able to bind ATP and hydrolyze it. And the TMDs here are in this region, so we recognize both TMDs. And the main characteristic of this transporter is this helix swapping between the two TMDs, 2 helices of one TMD being in contact with the other NBD. And this is made to have a good communication between the TMD and the NBDs. In this conformation, the ATP can be hydrolyzed, but the drugs cannot bind to the drug binding site, which is open to the extracellular space. So we suppose that the drug bind to the drug binding site here, and which trigger a large conformation change compatible with the alternating mechanism access. And the reset to the initial conformation is done by ATP hydrolysis. There is also now several structures which have been resolved, mainly open, in the inward facing conformation, as you can see, from some very widely open to rather closely, tightly closed. And some of them are apo, without anything. Few of them, one of them is with two inhibitors, two structures with one inhibitor, and more recently this year was released the first substrate, glutathione, in the TM1, and several of them have some AMP-PNP, so an analog of ATP, bound to the nucleotide binding region. So this structure maybe shows you what could be a movie of transport for the binding of drugs in this conformation to the release in that one. So BCRP, PGP, and MRP1 are characterized by the fact that they transport they can transport common drugs, like, for example, daunorubicin or mitoxantrone, and also have specific drug transported, like this one. So this means that it is rather difficult to reverse the multidrug resistance phenotype by only targeting one transporter. And secondly, when the resistance is conferred by one drug, for example, daunorubicin, it is conferred to all other drugs, to the other drugs transported by the transporter. So it's rather difficult to fight against this system. In terms of drug binding sites, in 1997-1999, Shapiro and Ling described in the PGP 3 drug binding sites, H, R, and P. H for the binding of UXT 33342 in competition with two other substrates. The R for rhodamine 123 in competition with daunorubicin and doxorubicin, and the P for prazosin in competition with progesterone. And they also described that these sites have a good communication between them, depending on the concentration of the drug bound to these sites. So either cooperative below 2 micromolar or in competition above this concentration, suggesting a good communication. So, of course, due to the importance of PGP, several inhibitors have been developed. This is the third generation ones, with some of them having reached the clinical phase, but still with a low clinical activity. Let us think to maybe there is other mechanism involved in this drug resistance, and maybe among them the action of other transporters. So in the lab, we have developed one series of inhibitors for the PGP using this dipeptide called reversin, made of aspartic acid and lysine. So a series was developed by Joël Paris, my colleague, chemist, this one. So among them, we characterized the efficacy, so rather poor for some compounds, better for other ones, and particularly this series of homoproline lysine, for which these compounds were really, really good, in fact. But unfortunately, it was too toxic. Not toxic, in fact, in vitro assays, but with mice, we could not use it, no longer use it, but use it to initiate this strategy by which we characterize the inhibition mechanism of this inhibitor and link to at this time the first structure which was released for the PGP. We found it mainly non-competitive for daunorubicin or efflux, and my colleague Raphael Terreux, using Sibyl, made the first trial of docking, showing that this inhibitor indeed bind to a pocket which is close but distinct to the drug binding pocket. But the serious thing started with the release of the 3D structure of the PGP, the mouse PGP, co-crystallized with the QZ59 inhibitor, so either the R or the S enantiomer, triple S or triple R enantiomer, in one copy for one structure, in two copies for the other, in another structure. This is a tricyclovaline, so ROS, with bearing 3 selenium atoms, making that at this low resolution we can really easily locate it in the structure. And of course it was rather exciting, and this first structure was quite exciting by the fact that we can at this time maybe started to locate the drug binding sites using this location of the drugs, of the inhibitors, if we could establish their inhibition mechanism. And we did that using a drug transport cell assay, and we set up, showing that with the R enantiomer of the QZ59, it behaves like a non-competitive mixed inhibition towards the efflux. Let us suppose that, conclude that the drug binding site and the inhibitor binding site are distinct, but at high concentration, it could share the same site. With donorubicin, we conclude to non-competitive inhibition, very clear, showing that both sites are distinct, not common, so I skip the secondary effects. And with the S enantiomer, we conclude to a competitive inhibition. This time with a very good inhibition constant, let us supposing that there is a tight overlap between the drug binding site and the inhibitor binding site. For donorubicin and the S enantiomer, we also conclude to a competitive mixed inhibition. Let us suppose at least for one drug QZ59 location, an overlap with the air transport site, and a non-competitive component. Let us suppose that there is another site for the QZ59 which is not the same as the air transport site. So with this new structure, we this time use not Sibyl but Autodoc and Vina, and these structures and these parameters, and looking at the structure of this, in which the QZ59S or S in green here are bound, or the QZ59R is bound, so maybe it's not clear, but it is not the same structure. It is two structures in which one compound has been added. Is it clear for you? So we dug the UXT 3342, and taking into account the enzymatic parameter we found, the best location, the best pose we found among the 15 was found along the groove in which the QZ59 are binding. So in good agreement with the enzymatic results. For the donorubicin, it was the same. We predicted a competitive and non-competitive behavior, so in two sites, and we found, in fact, the two main poses here, or the -13 and -12 kilocalorie, were found, one with in competition with the QZ59S binding site, the most embedded in the structure, so something here for in this region, and the other site close to the other QZ59, so non-competitive. So this led us to conclude that the H and R sites are close together but distinct, which is in good agreement with the findings of Vittorling early, which show this communication of the drugs, and depending of the concentration of these drugs, there is a competition or cooperativity. And now, so we having these residues identified, we are going to start a structure-based approach to design the new inhibitors, at least in this conformation. At least in this conformation, because this is a characteristic of this protein. It undergoes a very large conformation change, and just to illustrate that, I have shown this on this structure. So we have here four structures of the PGP, one in which the QZ59 is bound, And the three others here, there is three structure there, very close together, the same. In fact, they are stacked on, they are aligned on this part of the protein. And by eye, at least, you can see that they are the same, almost the same. But using this structure, so we perform a morphing study. When you see that the conformation change, at least reduced to this conformation here, is already very big. So you can see that the sites, the H in blue and the R in red here are moving a lot. So it's probably not so easy to design a specific inhibitor in that way, but we will try. So I turn to BCRP, which is somewhere a challenger of the PGP, for which we have carried out two studies. The first studies done in 2010 was to characterize the transport of porphyrin. And the second one, what we are doing now, is to try to localize the drug binding site of this protein by transposing the strategy we have done with the P-glycoprotein. So concerning the heme transport, in 2002 and 2004, it was shown that BCRP is able to transport phosphorbid-A, which is a metabolite of the chlorophyll, and protoporphyrin 9, which is a precursor of the M here. PPP9 is there, 9 is there, and heme is there. And heme, of course, you know that it is this compound is involved in a series of very important metabolic pathways, but is quite toxic in this ferrous or ferric form. Yeah. So this suggests to us at this time that probably since BCRP or BCG2 is able to transport this compound, it probably has to transfer it to a partner before to release it in the extracellular space. So we study this hypothesis and focus on the extracellular loop of the protein there, which is so a dimer of 2 times 80 residues. And we found a rather a given similarity with cytochrome B5, to which bind heme. For example, this histidine there and histidine there with this tyrosine. So we produce this domain in bacteria, removing the purification tag by the thrombin here, and check the folding of this protein by using a very nice tool, which is a conformational antibody 5D3, which recognizes conformation of the domain, and especially when this disulfide bond is oxidized. So indeed, when oxidized, we had a very tight interaction with the antibody and the domain here, and when we reduce it, we are no longer any interaction. So showing that the domain is rather good, rather well folded. We use this tryptophan here. There is 4 tryptophan in the domain to probe the binding of the heme and other compounds, as keep the others here. Compare, for example, to another drug which is transported by the BCRP, the mitoxantrone. So you can see that here we have a rather good interaction and no interaction there. Here in a micromolar range, which is rather modest, but not so bad, taking into account that if the porphyrin is transported, then transferred to the ECL3, it has then to be released to a given partner. In terms of partner, we suppose that the serobanbibin could be that one, since it is known that it binds heme with a rather good affinity, about 10 nanomolar, and a crystal structure has been obtained with heme. And to check that, we probe the binding of heme and its release by fluorescence. So it is shown on the domain alone here, or on the whole protein there. And we observe that, of course, a quenching of fluorescence with the binding of hemine, which was reversed by the addition of serum albumin. And it was not the case when serum albumin was preloaded with amine. So rather good. We observe the same here with the whole protein. So this suggests that serum albumin is able to bind to acyl-free, and there is a rather fluorescence quenching when HSA binds to acyl-free to do that, and take off the porphyrin. By absorbance, we could also check the removal from the acyl-free to the serum albumin of the porphyrin. So to finish, and at this time we are trying to localize the drug binding sites of BCRP. So it's not so easy, but we are because we have only a model of BCRP based on the PGP. But we are using common drugs, so like the UX33342, or common inhibitors, or specific one, and we are trying to see how the QZ59 are working in that context. And we have found that the QZ59R is this time competitive. It was non-competitive with the PGP, with rather good inhibition constant, while the S enantiomer is non-competitive at all. And looking at the gold standard KO143 and the gold standard for the PGP, the GF, so we also conclude for competitive inhibition in both cases, with very good inhibition constant here and there. So this indicates that probably all these compounds share the same site, the H binding sites in BCRP, and taking into account that the similarity in the transmembrane region, we think that the topology is the same. We are now starting a mutagenesis approach to check the validity of all these residues in the site, and of course later a simulation to have a better understanding of this. So this story stops there, and I thank you for your attention.
We still have time for one question. So, yeah.
These transporters must be extremely flexible.
Mm.
And how do you include, let's say, the flexibility in the rationalization of your ligand or substrate binding?
This is a huge question. This is a big question, of course. So, as we discussed yesterday, we maybe try to. So we have several conformations now. As you showed you, we have several conformations for which we can build model, but not simulation model, on which we can try to see how the drugs or the inhibitors can bind. We can also make some simulation, but I'm not sure that the simulation could be better than the test of the drugs or the inhibitors on all these models, on all these conformation. I don't know if I am clear, but so usually one could think that.
And do these approximate models indeed work for as a guide for the mutation and expression experiments?
You need for BCRP?
Yeah.
Yes, it's not okay. A model is a model, so it's always good. As far as we make some experiments to show that there is some mistakes, of course, but it's not so bad. So for the inhibitors, I think our strategy will be to build all the human PGP model built on this conformation, and we'll privilege this strategy among the simulation, if I am clear, because I think simulation is not clearly representative of the natural states, I should say.
Okay, thank you again.
Okay.